Hi students, welcome back for the second lecture of week 7. So now we're going to begin to talk about the ways in which we can describe the different types of reactions. So in the last lecture we learned about how to write down a chemical equation, which is the way to express a chemical reaction on paper. And we also talked about how to balance the chemical reaction to express how many atoms or molecules or units of an ionic compound are involved in the reaction. Now we're going to talk about what types of reactions there are. There's going to be different ways to describe them. These first 5 that are listed here are rather simplistic ways of describing chemical reactions based on the way in which the atoms rearrange how they're bonded. The last one, oxidation reduction, is a more complex way of describing reactions that describes what's happening to the electrons in the reaction, in the atoms in the reaction. And so let's begin by talking about these first 5. I'll list them one by one. So combination reactions are those that occur when 2 substances, which are generally elements, combine to form a compound. These are sometimes called combination or addition reactions. In these reactions, you'll have 2 reactants reacting to make one product. So that's how you can recognize them. There'll be two items on the left, 2 reactants, 1 on the right. So as a general example, you'll have element A, element B, their atoms combining to make a compound with atoms A and B in them. For example, here we have hydrogen reacting with oxygen here to make a compound that contains both hydrogen and oxygen, water. Or carbon here, which is like coal, charcoal burning in oxygen to make CO2. And so I have a few little cute cartoons that I got from someone else's slides here that I think are pretty nice for this. If you combine a skinny bird with a worm, it makes a fat bird. That's a combination. For a real life example here, we've got the element potassium, which is a silvery metal. When that is reacted with chlorine gas, which is this brown gas, you get a very violent reaction, a lot of light and heat energy released, and finally you get this white solid, which is potassium chloride, much like table salt. So a couple of things here. One thing to note is that if you look, just want to emphasize here that compounds that are produced from a reaction do not necessarily share any of the properties as the elements that compose the atoms that compose that compound, right? Potassium chloride is very, very different from this shiny, silvery potassium metal, and also very different from this brown chlorine gas because it's an ionic compound with very different properties. So just because potassium chloride is made from potassium and chloride ions, it doesn't really have any similar properties to potassium metal or chlorine gas. That's an important thing to note. And the second type of reaction we'll talk about is decomposition reactions. So these occur when a compound breaks up into elements with or basically simpler compounds. So the way you'll recognize it is there will be one reactant, but it will make 2 or more products. So in general, you have a compound here that contains both A and B type atoms, and then it separates into the elements A and B. So an example here would be the opposite of the reaction we saw earlier, water breaking up into hydrogen gas and oxygen gas. As you can see, a decomposition reaction is basically the opposite of a combination reaction. Another example, which is pretty dramatic and pretty cool, is mercury 2 oxide. When heated, decomposes into mercury, which is a liquid metal, and oxygen. So here's a cartoon. You have the turtle that's in the egg, and then it decomposes into an egg and a separate baby turtle here. So here's another example of a decomposition reaction. So it's the mercury 2 oxide that I mentioned earlier. This little delta means heat, and when you heat it up, this brown solid turns into the silvery liquid metal, liquid mercury, and oxygen gas, which escapes from the test tube here. So one thing I want to point out about the way this reaction is written, and something we're going to start doing pretty soon, is you might notice there's like parentheses S here, parentheses L, parentheses G. These are stating the phase or the state of the reaction. So mercury 2 oxide is an ionic substance, and generally those are solid, as we talked about last week. And you can see the little S is a solid there. The element mercury is a metal that's liquid at room temperature, the only metal that's liquid at room temperature. So it's indicated with an L here. And then the oxygen is flying out of the tube as a gas, so it has a little G here. So S for solid, L for liquid, G for gas. Okay, the next type is single replacement reactions. So these occur when one element replaces another in a compound. And this can happen in a couple of ways. If it's an ionic compound, a metal can replace another metal in the ionic compound, or a nonmetal can replace the nonmetal. The metals are generally positive ions, the nonmetals are negative ions. So this doesn't have to be ionic compounds that do this, but it's important to mention what happens when it is an ionic compound. So basically an element will be reacting with a compound and two products will be made. A general form of this would be if A is a metal, generally in the ionic compounds, the metal's written first, the positive ion, the non-metal's written second. And so the metal A here would replace the metal B, and then you'd have a compound with the atoms A and C and B in there. Or if A is a non-metal, then it will replace the non-metal negative ion here in the compound, and so A will replace C, and you get a compound with atoms B and A, and C now will be by itself. So remember that the cation or the positive ion is always written first, so B here was the positive ion in that compound. And a cartoon to represent this here, this guy, he's single, and there's a compound here, our dance partners, but then he butts in and he goes with this girl here, and now he's single. So it's a single replacement. He was single first, but now he replaced the other guy, and now the other guy is single. So an example of a single replacement here is the lithium atom replacing hydrogen and water, and you get lithium hydroxide, so it replaces one of the hydrogen atoms. The hydrogen atom leaves as hydrogen gas. And so this is in fact, this is what's known as a base lithium hydroxide, or an alkali. This is in fact why group 1 atoms like lithium are called alkali metals, because when you combine them with water they make a base. You don't got to remember that, but that's just a little trivia for you. Another thing is about phases. We see solid, liquid, and gas again. There's another one here, AQ. So AQ stands for aqueous. It means dissolved in water. We're going to be talking a lot more about aqueous phase and all the phases in the next lecture. Okay. And finally, the last type, double replacement. I'm going to go over double replacement briefly because our whole next lecture is going to be about all the different types of double replacement reactions. These are also sometimes called metathesis reactions. They call it that on your experiment 4. So double replacement reactions happen when basically atoms switch partners. So a metal replaces a metal in a compound, and a non-metal replaces a non-metal, usually when it's ionic compounds. So generally you start with two compounds, you get two products here. So A is in a compound with element B here, and C is in a compound with D, but A and C trade places, so that A is now with D instead of B, and C is now with B instead of D. So here, an example of a double replacement in cartoon form. These guys switch hats, and so now this guy has a new hat, and this guy has a new hat too, just like the A has a new hat, it's D, and the C has a new hat, it's B. And we're going to get lots and lots of examples of double replacement reactions in the next lecture, but I'll also show you an example in this lecture before we're done here. The fifth type is a little bit different from the rest. It's combustion. So combustion is a very specific type of reaction. It's a reaction that occurs when a hydrocarbon, which means a molecule that has hydrogen and carbon atoms in it, reacts with oxygen gas. So an example of a hydrocarbon would be methane, CH4. That's like natural gas, basically. That's what comes out in the Bunsen burner or your stove, and that reacts with oxygen here. And when it does, to make it burn, you need three things to have a fire, basically. You need the fuel, which is the hydrocarbon. You need oxygen for it to react with. And usually you need a spark to get it going. In general, the reaction is written like this. A hydrocarbon, so CXHY, means you've got a molecule with carbon atoms and hydrogen atoms in it. Sometimes there's also oxygen atoms or other atoms, but it's usually mainly carbon and hydrogen. These react with oxygen, O2, and make carbon dioxide and water. So oxygen is always the other reactant, and the product in combustion reactions is always CO2 and water. So these ones are pretty simple to pick out. Just look for the oxygen as a reactant and CO2 and water as the product. Now, you may be wondering, okay, if combustion or burning always happens like this to make CO2 and water, CO2 is a clear gas and water is just, a clear liquid. How come when we see like a car driving, there's this black stuff on the tailpipe? What's going on there? Well, it's because in an engine, often there isn't enough oxygen to completely react with the hydrocarbon. And so often you'll get other products such as carbon monoxide, which is CO, or just, chunks of carbon. This is the black soot that you see. And so, combustion doesn't always go this cleanly if there's not enough oxygen there. But we use it all the time, so it can make some dirty stuff. It makes CO2, which is a real problem for our atmosphere. You guys probably heard about that, climate change. We'll talk a little bit more about that as we move forward in the class. It's a really important topic. But we use burning for all kinds of things to get energy. Combustion is a very, very important reaction to human beings, although it is dangerous. We all are required to have carbon monoxide detectors in our homes now, or in rental properties, because if incomplete combustion is happening in a water heater or something inside, and carbon monoxide leaks into the home, you can be suffocated by it because it takes the place of the oxygen in your blood cells. So combustion, a very important reaction, also with its hazards. So finally, we've talked about the different types of chemical reactions, and now I want you to try to identify these different types of reactions here based on what you see here. So I encourage you, if you're watching the video, to pause it here, maybe take a look back and remind yourself, and try to answer these on your own. So after you pause it now. Okay, so hopefully you've tried these on your own, and we'll get some answers here. So here, if we look at this first one, we see the silver is here with the nitrate in this compound, and the sodium was with the chloride. But after the reaction is over, the silver has traded places with the sodium, and now it's with the chloride, and the sodium has traded places with the silver, and now it's with the nitrate. And so this is a double replacement reaction. The silver and the sodium switch places here. In the next reaction, we have an element, lead, and then we got silver nitrate. But after the reaction is over, the silver is no longer with the nitrate. It's actually single all by itself. The lead has taken its place. This is a single replacement reaction. In the next one, we have a C2H4. This is a hydrocarbon molecule. It's reacting with oxygen, making CO2 and water. So this, if you see oxygen as a reactant, the product CO2 and water, the other reactant being a hydrocarbon. This is a combustion reaction. Finally, here we have the element nitrogen reacting with the element hydrogen. It makes a compound NH3. So these two are combining into a compound. This is a combination reaction. Combination. And so you should be able to do that on the homework. I've got some where I tell you to identify the reaction and also to balance it. Finally, we're going to talk about the last way in this lecture of describing reactions. This is in terms of oxidation and reduction. Now, in your book, they do tell you about how to assign oxidation numbers. You can do it that way if you like, but I'm going to give you an easier way than your book does to identify what's happening in an oxidation reduction reaction, and it will not require you to assign oxidation numbers. I think it's a little bit easier, and it's also applies better to the for those of you that are going to be taking biology classes. You don't really usually assign oxidation numbers in there either. You look at it in this fashion. So I think that talking about it in this way is a little bit better than most chemistry books talk about it. And so this is the way I'm going to present to you oxidation reduction. It's a bit different from what's in your textbook. So we're going to talk about oxidation reduction instead of assigning oxidation numbers in terms of gain or loss of oxygen atoms. That's actually where the term oxidation came from. It originally corresponded to the gaining of oxygen atoms. But now oxidation reduction has a much broader definition, so we can also refer to oxidation and reduction in terms of the loss or gain of hydrogen atoms. And then the broadest definition of oxidation and reduction is in terms of the loss and gain of electrons, and that's the technical definition now of oxidation and reduction. Whether oxygen is involved or not, it has to do with the losing or gaining of electrons by a substance. So let's start with referring to what's happening with the oxygen atoms. So we're going to say if a compound or element gains oxygen atoms, we're going to say that it's oxidized, or oxidation has occurred there. If you lose oxygen atoms, we're going to call this reduction. So this is kind of the oldest definition of oxidation reduction. The word oxidation, again, came from the recognition that oxygen atoms were gained by a substance. So let's take a look here at this example reaction. So here we have carbon monoxide reacting with oxygen gas to make CO2. So we analyze this and we look and we see, well, carbon monoxide originally had one carbon atom and one oxygen atom. But when it produced the product that was produced has a second oxygen atom instead of just one. So this CO, so we say, what happens to CO? It gained an oxygen atom to make CO2. So what you're doing is looking at the reactants and seeing what happens to them. The CO gained an oxygen atom. So we say that it was oxidized. What happened to the O2? Well, the O2 was the source of the oxygen atoms, all right? So the oxygen atoms came from the O2, and then they attached themselves to the CO so you can make CO2. So since the oxygen atoms came from the O2, we could say that the O2 lost its oxygen atoms. So that, in that sense, it was reduced. So what you want to do when you're identifying oxidized or reduced is to notice what happens as the reactants change from reactants to products. The CO gained an oxygen atom. Where'd those oxygen atoms come from? The O2. So the CO was oxidized by gaining oxygen atoms. The O2 was reduced by losing those oxygen atoms or providing them. Another example here, this is formaldehyde, like what's used to preserve frogs or whatever for dissection. And this is hydrogen peroxide, also called dihydrogen dioxide. So here, when we look at the products, we can see that the H2CO now is H2CO2. the H2CO has gained an oxygen atom. So we would say this gained oxygen going from here to here. So we would say that this is oxidized. Okay. Now, where'd the oxygen atoms come from? The H2O2. Now it's only H2O. It lost an oxygen atom. So this lost oxygen atoms going from here to here. So we would say that H2O2 was reduced. So which reactant gains oxygen? It's the H2CO. It gained oxygen, made H2CO2. Which reactant loses oxygen? It was H2O2. Notice which reactant. The terms oxidized and reduced only apply to reactants. This is important. When I give you a multiple choice question about this on a quiz or a test, I'm going to give you 4 choices. You can immediately eliminate the products. We never describe the products as oxidized or reduced, because the point of saying oxidized or reduced is to say where the reaction is going, what products are going to be made. Once you're already at the products, the reaction is over. So it has nothing to do with describing what was oxidized or reduced. When you describe what's oxidized or reduced, those are terms that apply to the reactants, telling you what's going to happen to the reactants when they make the products. Burning is always an oxidation reduction reaction. When you burn something, you're reacting it with oxygen. So, like wood or paper or hydrocarbons, whatever, these are reacting with oxygen. So they're gaining oxygen atoms from the air. So oxygen is being reduced by providing the oxygen atoms, and the wood or the paper is being oxidized. So burning is an oxidation process. Burning is in fact where the word oxidation came from. It was discovered that when things burn, they're gaining oxygen atoms, so they're being oxidized, and the oxygen is what's being reduced here. It's providing the oxygen atoms. Now, the other way to talk about oxidation and reduction, which is very important in your biochemical or biology classes, is the loss and gain of hydrogen atoms. So the loss and gain of hydrogen atoms in describing oxidation and reduction goes opposite to the oxygen atoms. So whereas gaining oxygen atoms is oxidation, losing hydrogen atoms is considered oxidation. And gaining hydrogen atoms is considered reduction. So let's look at an example. So in this reaction, carbon monoxide is reacting with hydrogen gas and making CH4O. So in this process, the CO gained hydrogen atoms. It attached to the hydrogen atoms from the hydrogen molecules. So which reactant gains hydrogen? It was the CO. It didn't have any hydrogen, but now it is combined with hydrogen atoms. So since CO gained hydrogen, we say that it was reduced. So I'll say gain H going from here to here. We say this is reduced. Now, the hydrogen is providing the hydrogen atoms. So this is essentially losing its own hydrogen atoms. So it's providing them. So we say that this was oxidized. It lost the hydrogen to make the CH4O. So it's combined here, basically. So again, what we're doing is we're watching what happens as the reactants change to products, and reduced and oxidized are terms that only apply to reactants. Now, for those of you that are going into the healthcare professions or into the life sciences, why would you want to know about this? It's because it's actually extremely important to metabolism and the way in which the body processes various substances. So right here, this is an example of the 6th step in the citric acid or Krebs cycle. So this is the main process for metabolism in all organisms that are not plants, from the smallest bacteria up to our own bodies. Super important process. It starts with a molecule called succinate, which has these kind of ion parts that are negative on the side, and then it has in the middle 2 carbon atoms that have 2 hydrogen atoms attached to them. So there's a big molecule. Now what happens is that these 2 hydrogen atoms here are lost, and it makes what's called a double bond between the 2 carbon atoms. But what you need to know is these 2 hydrogen atoms are lost. They attach to a molecule called FAD, which is this is a shorthand for a very big molecule with lots of atoms in it. But the 2 hydrogen atoms are lost from the succinate, and they attach to the FAD. So since the succinate loses 2 hydrogen atoms, and we say that it was oxidized here. The succinate is oxidized because it lost hydrogen. The FAD gains 2 hydrogen atoms, so we say that it was reduced because it gained hydrogen atoms. And so when you learn about the citric acid cycle, it's going to be a very important part of the cycle. And again, your book goes into assigning oxidation numbers. If you're going to go on in chemistry, you'll learn how to do that in Chem 150. But for those of you that are not going to be taking general chemistry, this is the best way to understand oxidation and reduction, because it's what you're going to encounter in your future classes. And you're not going to be assigning oxidation numbers to evaluate what was oxidized or reduced. So we talked about now gaining and losing oxygen atoms and gaining and losing hydrogen atoms. Those are the ways of describing oxidation and reduction for covalent compounds. For ionic compounds, well, they're going to be forming ions. And so the way that we're going to evaluate what's going on is based on the movement of electrons. So we're going to say that if electrons are lost, we have an oxidation. And if electrons are gained, we have a reduction. A little mnemonic for that is Leo says Gur. Losing electrons is oxidation. So losing electrons is oxidation, Leo. Gaining electrons is reduction, Leo says Gur. And so that's one way of evaluating it. I'll also show you a kind of simpler way too for ionic compounds evaluating it. But let's just look at individual ions and break these into metals and nonmetals. So when metals make ions, they make positive ions by losing their electrons. And remember, losing electrons is oxidation. So this is a loss of electrons. We also call, see the charge here, positive one, we also call that the oxidation number. So we're not going to have to assign oxidation numbers, just think of the charge. So the other way I think of oxidation is that if the charge goes up, this charge is 0 here, it's not written, but the charge is 0. It went from 0 up to positive 1. When the charge or the oxidation number goes up, that's oxidation. And that happens because an electron is lost. The lithium lost 1 electron when it made this ion. The opposite of that, when a metal ion goes back to being a metal atom, this happened because it gained an electron back. So here, the lithium ion didn't have its valence electron, but when it gains it back, it makes the lithium atom, and it has been reduced. The way I think of reduction, kind of more simply, is that the charge gets reduced. It goes down from positive 1 to 0. I think of that as reduction. That's kind of a quick and easy way to think about it as well. The charge went down from positive 1 to 0 because the lithium gained an electron. Gain electron, reduction. Charge goes down, reduction. Now what about for nonmetals? So let's take the nonmetal, fluorine. Now fluorine comes in molecules like this, F2. Okay, this is what's called a Lewis structure for a molecule. We're going to be doing those a bit later. But each of these fluorine, total there are 14 valence electrons. Each fluorine has 7. But then to make an ion, there's 0 charge here, 0 charge, okay? To make an ion, each fluorine gains 1 electron, and it makes a fluoride ion. So the oxidation number, or the charge now, is -1. And so the charge has gone down. I think of that as reduction whenever the charge goes down. Or think of gaining electrons. Each fluorine gained an electron to get a negative charge. Gaining electrons is reduction. The opposite, when a nonmetal ion becomes a nonmetal atom, here it goes from having a negative charge to having 0 charge. Okay, so you'll find a nonmetal ion as a part of an ionic compound like potassium fluoride or lithium fluoride. That's when it's in ion form and it's negative. If it loses its electrons, it will make a nonmetal atom. These are nonmetal atoms bonded together, and that is oxidation, because it's losing the electrons. Or the other way to think of oxidation is the charge goes up from -1 up to 0. So remember that for ionic compounds, these are composed of individual ions, and so you can think of the charge of the individual ion, and it's changing when it's no longer an ion. So here's an example. Here we have a metal atom, okay, with 0 charge. And we have nonmetal atoms here also with 0 charge. But then they make an ionic compound. And we should break this apart and look. What are the ions in here? There's a lithium ion in this ionic compound. It's +1. And there's a fluoride ion. It's -1. And so here the lithium the lithium lost its electron to make a positive ion. So here, it lost 1 electron. That's oxidation. Loses 1 electron. That's oxidation. So the lithium was oxidized. Okay. Or the other way you can think of it is the lithium went up in charge from 0 up to +1. Going up in charge is oxidation because you go up in charge when you lose electrons. Now on the other end here, the fluorine gained electrons. Gain electrons. This is reduction. The fluorine was reduced. Okay, or you can think of it like the charge went down from being no charge to being -1. When a metal atom becomes a metal ion, it becomes positive and it's oxidized because it lost electrons. When a nonmetal atom becomes a nonmetal ion, it's a negative ion because it gained electrons. It's reduced. Okay. Or again, you can think of the charges of the oxidation number too. Oxidation number went up for lithium. That's oxidation. Oxidation number or charge went down for fluorine. That's reduction. Here's another example. So again, think about the nonmetals going from atoms to ions and vice versa here. So here, this is an ionic compound. I can tell because it has a metal and a nonmetal. So I should think about what ions are in here. Well, it's K+ is the positive ion and Br- is the negative ion. But this is a nonmetal atom. No charge for this. Okay? There's no charge. It's not an ionic compound. Okay? Same for the bromine here. There's no metal in here. This is not an ionic compound. It has no charge. But this is. It has a metal and a nonmetal. So it's composed of K+ ions and fluoride ions. So here, this fluorine went from being 0 charge down to being -1 charge. Okay, so this must have gained electrons. This was reduced. Or you can think of it as going from 0 charge down in charge to -1. That's reduction. Now, the bromide had a -1 charge as an ion, but it went down to 0 charge as bromine. Okay, or sorry, it went up to 0 charge rather, because it was negative and it went up to 0. This happened because it lost electrons. It lost electrons. That means it was oxidized. And one important note here is that notice nothing happened to the potassium. It was +1 charge before, +1 after. But it's oxid. So I have to rewrite that. One thing I want, oh shoot. One thing I want to point out though, oxidized, there we go, is that when we describe what is oxidized or reduced, it's very common to refer to the whole compound. So we say this KBr was oxidized, even though the potassium really had nothing to do with it. It didn't change charges at all. And we say that the fluorine F2 was reduced, okay? So here, the F2 is a nonmetal making an ion, which is negative. It gained electrons. It's reduced. The KBr was a nonmetal. It had bromide, which is a nonmetal ion, forming nonmetal atoms. This is because it lost electrons and went to a higher charge, 0. So it was oxidized. So in summary, for covalent compounds, you can use the gain or loss of oxygen to determine, or hydrogen, to determine if it is oxidized or reduced. So these two are useful for covalent compounds. And then these two here are useful for ionic compounds. So if a covalent compound gains oxygen, that's oxidation. If it loses oxygen, that's reduction. If a covalent compound loses hydrogen, that's oxidation. If it gains hydrogen, that's reduction. For ionic compounds, if a metal atom becomes a metal ion, it's going from 0 charge to positive charge. That's oxidation. Okay. If a metal ion becomes a metal atom, it's going from positive charge to 0 charge. That charge is going down. That's reduction. On the other hand, if a nonmetal ion becomes a nonmetal atom, it's going from having a negative charge to having 0 charge. So the charge is going up because it's losing electrons. That's oxidation. However, if a nonmetal atom with no charge becomes a nonmetal ion with a negative charge, the charge is going down because electrons are being gained, and so you have reduction. And so this is the final summary for the oxidation and reduction. One more piece of information though. Unfortunately, there's extra terminology associated with this. So if a substance is reduced, we call it the oxidizing agent. I know, this is terrible. It wasn't my idea. Why is it called that? It's because oxidation and reduction always happen together. So if a substance is reduced, that means it gained electrons, but it must have gotten those electrons from somewhere. It got it from another compound that gave them away. And so the substance that is reduced causes the other substance that it reacts with to become oxidized. So the substance that is reduced is called the oxidizing agent. Conversely, if a substance is oxidized, that means it lost electrons, which means something else must have gained electrons and been reduced. So the substance that is oxidized is referred to as the reducing agent, and the substance that is reduced is referred to the oxidizing agent. I know, it's terrible, but it's important that you understand this terminology because it's very, very commonly used. Along with, so the reduced thing is the oxidizing agent. The oxidized thing is the reducing agent. Yes, it doesn't make anyone happy, me included. So here, again, when we have combustion, the oxygen always supplies the oxygen atoms. So here, the CH4 is being oxidized because the carbon now is gaining oxygen atoms. That means, and the oxygen's reduced because it's supplying the oxygen atoms. It's giving them away. So that means since the CH4 was oxidized, it is the reducing agent. And since the O2 was reduced, it is the oxidizing agent. Oxygen is a great oxidizing agent. It provides the oxygen atoms. It gets reduced. So, yes, that is the unfortunate terminology that we're dealing with. So let's identify the oxidizing agent and the reducing agent, and also what is oxidized, what is reduced. If you want to pause here and give this a shot yourself, I highly recommend it. Go ahead and pause now. Okay, let's talk about the answers. All right, so here we're making an ionic compound here, and we've got metal atoms, we've got non-metal atoms, so we're going to want to use the ionic way. So these are metal atoms, you know, we can write the charge if we want. There's zero charge on these, but they're making an ionic compound here with nickel. Okay, so nickel here is going to be, in this case, 3+, and the iodide here is I-. Okay, so we have a metal atom becoming a metal ion. Its charge is going up, it's losing electrons, it is being oxidized. And we have a non-metal atom becoming non-metal ions, its charge is going down, it is reduced. Which makes the Ni the oxidizing agent, or sorry, the reducing agent, because it was oxidized. Reducing agent, because it was oxidized. So the nickel is the reducing agent. The iodide, because it was reduced, is the oxidizing agent. Okay, another example here. C2H4 reacting with H2, making C2H6. This is all covalent compounds, and we can see that hydrogen is being gained. So we should use the hydrogen gain or loss. So here the C2H4 is gaining hydrogens to make C2H6. So since it's gaining hydrogens, we say that it was reduced. So the C2H4 was reduced, which makes it the oxidizing agent. Oxidizing agent. Now the hydrogen is providing the hydrogen atoms. It's giving the hydrogen atoms. So by losing the hydrogen atoms, it itself is oxidized. So we would call it the reducing agent. And finally, iron oxide is reacting with carbon monoxide, making iron and carbon. So this has ionic compounds and covalent compounds. We could do this either way, but I can see that the iron is losing oxygen and the CO2 is gaining it. So I can use the easier oxygen way here. So since the iron is losing its oxygen atom, losing an oxygen atom is reduction. So this is being reduced. And the CO is gaining an oxygen atom to make CO2, and so it is being oxidized. And so that makes the iron 2 oxide, since it's being reduced, it is the oxidizing agent. And since the CO is being oxidized, it is the reducing agent. Okay, and that is the end of this lecture about the various types of reactions and based on the movement of atoms and also oxidation and reduction. In the next lecture, we're going to focus on the various types of double replacement or metathesis reactions. and we're going to be able to predict the products of those reactions. So I will see you in the next lecture.